Bismillahirrahmanirrahim. Alright, class, Assalamu alaikum, and welcome to the third lecture of week 8, where I just want to discuss a very supplementary topic, but really very important relationship regarding the divergence, and that is divergence theorem. And in the last lecture, we concluded, when we were discussing divergence, we concluded this equation, okay, that the closed loop surface integral of this d dot ds is equals to the total charge enclosed by that closed surface integrated over the volume which is occupied by this closed surface. So the total volume within this closed surface will carry this much amount of charge, and if that charge is generally represented in the form of volume charge density, so this equation holds. So since we discovered at the end of the chapter number 3 that Maxwell's first equation as related to electrostatics is given by divergence of electric flux density is equals to the source density, which is charge density. So if I replace this fact over here in equation number 1, I'll get this very important relationship in which on both sides of the equation we have got the field, which is electric flux density. Here we had flux density on one side and charge density on the other side, but here we have got flux density on one side and flux density on the other side, which are related by divergence, I should say. So on one side, on the left hand side, we have got surface integral or two-dimensional integral or two-variable integral of the electric flux density field, which is equals to somehow, and how we have already discussed, which is equal to triple integral or three-dimensional integral or three-variate integral of the same field which is given on the right hand side. So this is a very important relationship known as divergence theorem, relating a two-dimensional two-variable integral to three-dimensional three-variable integral. By the way, the only relationship which you would see between these two, or connectivity, or not the relationship but the connectivity between these two terms, is that this volume and this surface integral are intimately related, such that this volume is actually the volume occupied by this closed surface. So if it is so, if this surface and this volume is so related that this volume is actually the volume occupied by this surface, only then this divergence theorem can be applied to the same field. Okay, otherwise this equality would have no meaning. If this is some other volume and this surface is some other surface which is not occupying this volume, then this relation has no meaning. So always remember that divergence theorem is applied only to such cases where the volume is occupied by the closed surface. Okay, so now with this we can start chapter number 4, which is energy and potential. So there are a few things which I should emphasize before starting this chapter, that wherever there is a force field, whether gravitational pull, due to gravitational pull, or due to electrostatic field, wherever there is force field, there is a potential field always associated to it. So let's say we have got this planet Earth, and we know that if I put a mass which also has gravity around that small mass, that gravity will interact with this gravity such that that mass will be pulled towards this the center of this planet. So if I take all the points and find the direction of force, what I'll get a force field. And we all know from our intermediate physics that if I want to move a mass in this gravitational force field, I'll have to apply some energy, and that energy will be stored in this mass, either in the form of kinetic energy if that mass is moving, or in the force in the form of potential energy if that is a static and maintaining some height with respect to the surface. So if I'm at somewhere, billions of light years away of any planet, whereas negligible or no influence of any planet or heavenly body whatsoever, and if over there I have a mass m, and if I try to move it around, definitely the amount of work which I'll have to do would be zero. Why? Because there is no force field around that. A simple, a very small push of maybe 0.0000001 millinewton will be able to move this mass for maybe perhaps billions of kilometers. It does not mean that कि हम स्पेस में जाके कोई सुपरमैन बन जाते हैं जो इतनी सी एनर्जी जो है वो इतने बड़े मास को जो है वो किलोमीटर तक लेके जा रही है. So that means that this definition of work, which is force into displacement, is valid under certain force field. It is not valid everywhere. So if that is the case, so we know that we have got the force field and how we define potential field within this gravitational field, which is mgh. Okay, potential energy is mgh. So let's see how can we define a force field in the case of electrostatics. All right, so for that I just want to give you the I would just want to ask you that if I'm talking about energy and from energy potential, so energy is fundamental and potential is something derived from energy. It is also energy, but generally it's a type of energy, you should say, because kinetic and energy is another type. So potential is some innate, latent ability of a body to exert energy. That's the potential. All right, so if I want to talk about energy, first thing I should talk about is work done, and we all know that work done is nothing but force applied on somebody multiplied by the displacement which happened in the position of that body. If I have a body like this whiteboard, if I keep applying force on it and if it is not moving, so work done is zero. It does not matter how much force I am applying. If this whiteboard or this body is not moving, the work done is zero. Similarly, if something is moving just by virtue of some proper physical properties and no force is being applied on it, in that case as well the work done is zero. So this is okay. So let me give you an example. Let's say I have this your textbook, Electromagnetics, William Hyde book, okay, and let's say I'm standing and facing the wall in front of me, and there is a wind force coming from there, okay, and if I want, my target is to move this book from this point to that wall while the wind is coming with huge force from my front side. So let's say this is the situation, this is the wall where I have to take this book, and somehow this wall is something made up of some net maybe. So wind is gushing from right to left in this direction, and the force of this wind is, let's say, along these black arrows, and I am here standing here, so I'm not showing myself. Let's say this is the book, and consider that this book is very extremely thin. Maybe it's so thin that its thickness is negligible. So I should better draw one line just to show you that this book is very thin, and my target is to keep take this book from here to here, meaning this is the displacement which I have to cover. So the force which I'll have to apply, I'm applying the force on the book in this direction, will be maximum if the orientation of the book is just like this, perpendicular perpendicular to the direction of the force. So if this is the force applied by me, so this will be maximum. Okay, let me call it F max. But somehow if I change the orientation of the book and now apply the force in this direction, if I have changed the orientation of the book, and now if I'm applying the force, this is force applied. Okay, so the force which I'll have to overcome to move this book from here to here, considering that the thickness of the book is almost zero, the force which I'll have to apply, I will have to overcome, will be a minimum here. And how much minimum? Zero, because the force which is being applied on the book would be zero. Consider that there is negligible gravitational force and no other force whatsoever. So in this case I'll have to overcome the maximum force, and in this case I'll have to overcome zero force. But moving in this direction would not solve my purpose, because I have to move I have to move this book from here to here. This is my destination. So how about if I make some angle? Okay, instead of moving book in this direction or in this direction, if I move the book in this direction, okay, if this is the force which I have to apply, how much force should I overcome? How much force should I overcome? So definitely, if the surface area of the book is perpendicular to the direction of the force experienced by me, or the force applied by the wind field, will be maximum. If I tilt the orientation, now in this case the force applied by me would be zero, or the force applied by the wind field will be zero. I don't have to overcome any force. But what if I make some angle like this, or if I make some angle like this and start moving? So definitely, since the area of the book experienced by the force will be reduced, so the force which will be experienced by me, which will be experienced by me, will be the force itself, force of the wind. I'm just writing that force. Fe is the force experienced by me, dotted with, if I move in this direction, dotted with AL. If AL is the direction in which I am moving, in this case it would be AL. In this case AL would be this direction. In this case AL would be this direction. So you can see that if I take the dot product, if I take this case, so the force experienced by me will be zero as predicted, because now force and the direction in which I am moving has got an angle 90. So force experienced by me will be zero. And if I am moving in this direction, so the force which will be experienced by me, if this is direction AL, so force which will be experienced by me will be given by this. Okay, so I have made an error deliberately just to show you why. Things will be clear. So this is the direction of force, so magnitude of the force of the wind, and this is my direction. Magnitude of AL is 1, so I am not writing it. That's it. and cos of angle between the two. So force is in this direction, and if AL is defined in this direction, so the angle is 180. So magnitude of force multiplied by magnitude of, in order to evaluate this, magnitude of force is this, multiplied by magnitude of AL, which is 1, multiplied by cos of angle between the two. So the angle of force is this. So as direction of force is from right to left, direction of movement is from left to right. So cos of 180 will be minus. So it means that I am doing some fundamental problem in defining the force experienced by me in terms of this. Is it? Is it? Am I doing any fundamental problem here? Fundamental is there any fundamental error which I am doing? Yes, because this is not the after evaluating this, what I'm getting is the negative of the force which I'm experiencing. I should get only magnitude of the force. It means that the fundamental problem with this diagram, not this definition, but this diagram, is that I am taking the direction of motion in the direction in which I am moving. No, I should not take that as the direction AL. Rather, I should take the direction opposite to that, or in other words, maybe it's not clear from here, or in other words, instead of taking AL in the direction in which I am moving, I should take that AL is actually the direction in which the force is moving, in which the or opposite to the direction in which I am moving. I should say it better like this, or in other words, perpendicular to the surface, but not in the direction of movement, rather opposite to that. Okay, so force experienced by me will be equals to the force applied by the wind dotted with AL, where AL is the direction of a direction opposite to that of the direction of motion. So if I would apply force in this direction, so AL would be in this direction. If I will apply force in this direction, AL will be in this direction. If I will apply force in this direction, AL will be in this direction. Okay, only then I will be able to get the force experienced by me. Otherwise, this force experienced by me, if I would evaluate this dot product, I'll get negative of the value which I should get. Okay, so this is the force, magnitude of the force which will be experienced by me if I move in this direction, in one direction. This is a force which is experienced by me. How about this Q? How about this F? So now, so far we are discussing, mechanical problem. If I want to make it an electromagnetic problem, and let me consider that this is electric field intensity, okay, and I want to move a positive point charge here in this field. Okay, so the force which I'll have to apply will be equals to electric field which will be applied, which is present here, multiplied by the charge which is I'm trying to move from within this field. Okay, so had this been a point charge, and had the source been has the source been this the field been the field of a point charge, so definitely here I would have a source charge, and I'll get the field emitting from the source charge, and this is the test charge which I am trying to move. So definitely the force experienced by this charge will be given by this well-known expression. Okay, so electric field intensity due to this is given by Qs upon 4 pi epsilon naught r magnitude cubed into r. So just replace E here, you will get the Coulomb's formula. Okay, so the force in any case on this charge, whether this field is emitted by a point charge or some other charge arrangement, force experienced by this charge will be equal to the magnitude of the charge multiplied by the field itself. So I can say that generally the force on a charge is given by this formula, where this E is from some source that can be in any arrangement. Okay, how to find E for 0-dimensional, 2-dimensional, 3-dimensional, 4-dimensional, 1-dimensional distributions? We have already discussed that. So if I want to find force experienced by me, if I want to move this charge from one point to another point, what I'll have to do, I'll have to evaluate this, which is, just replace it here, I'll get this. This is the magnitude of the force which I will experience. So the magnitude of force which I'll have to apply should be at least equals to the force which I'm experiencing, or only then I'll be able to move it. Okay, so if this is I'm experiencing, so this should be the force which I should apply to overcome the force which I am experiencing due to this field. And as soon as I surpass this field, this force by minuscule amount, differential amount of force, as soon as I surpass a minuscule differential amount of force with respect to this force which I am experiencing, I'll start to move in the direction opposite to that of the field, itself. जैसे ही मेरी फोर्स इसके बराबर होगी और बारीक जर्रे जितनी बड़ी होगी, I'll start to move. So this is the force which I'll have to overcome. Okay, so it means that if this is the case, so how much amount of differential work should I do in order to move this charge from one point to another point? If I am moving in this direction, okay, so how much amount of work should I do if this is the distance in which I am moving? So I'll have to force applied, work done is force applied multiplied by displacement. Force applied is this, multiplied by displacement is dl. So what is this? This is the differential length in vector form, minus q e dot dl. So this much amount of differential work is what I have to do on this charge in order to move this charge in the field by this distance. So okay, how can I make my work 0? I can make the work done 0 by some trivial cases, like if I some stupid cases I should say, that I make the charge which I am moving 0. तो फायदा क्या हुआ सारे डिस्कशन का? That's a trivial nonsense kind of case. Or I make the field 0. Again, if there is no field, no work done. Okay, that's a nonsense. If I decide not to move a charge, dl distance, if I decide not to move the charge at all, so I'm keeping the charge here, that's it, no movement, no displacement, no work done. So these are the nonsense kind of case, but there are some really important cases which we should take care of, in which neither Q is 0 nor E is 0 nor DL is 0, but there are few cases in which we can get the work done 0, and that case will come through the property of dot product. If I move in some direction in which the direction of the field and direction of motion is totally orthogonal to each other, perpendicular to each other, meaning if I decide to move in this direction or this direction, just as I gave the example of the book, if I'm moving in this direction or this direction and wind is coming from my front, if I move in this direction, upward or downward, keeping the book like this, downward, upward, no work will have to be done in this case. So it means that if I move a differential, now remember, when we talk about differential, it means that we are talking about 2 points side by side. Okay, you can imagine it like this. Okay, so very minuscule distance, no distance can be smaller than this one, no distance can be smaller than this one, no distance can be smaller than this one. Okay, you should remember that. So if you want to find the work done the work done to move a charge within this field, a distance of dl, जिससे छोटा कोई distance नहीं हो सकता, we cannot have any distance smaller than this one, the amount of work done will be this one. इससे छोटा फिर work भी कोई नहीं हो सकता for this charge and this field. So we won't be able to get any work smaller than this for this charge and this field if we have decided to move this charge within this field. How much? This much distance. So we cannot get a smaller value if we have decided a smaller value of work if we have decided to move this charge in this field. Okay, definitely this will be in joules because we are talking about energy. So how about the total work done in moving this charge in this field some macroscopic distance? Definitely mathematically you would say that just integrate it, integrate this equation, you will get this. Okay, why I took Q out? Because throughout my journey I haven't changed the value of Q. If I want to move a point charge from here to here, so throughout this journey I haven't changed the value of Q, so I can take it out of the integral sign. So this is the total work which I'll have to do while moving a point charge Q from here to here in the field, electrostatic field E. So integrate it from the initial point to final point, and definitely the units will be joules, work done will be in joules. Okay, so now if that's the case, so is there any important cases on which we can apply this? Let me rub the board and we'll discuss. Alright, so I have named this equation 2 and this equation 1. So if I just break this dot product, what I'll get, I know that this dl is nothing but the distance in which I moved, that magnitude, and the direction in which I experienced the force. This is the direction. This is not the direction in which I moved, remember. Okay, so anyway, this is this. All right, so okay, so this is equals to this, and if I take this dot product, what I'll get? I'll get the direction of the field, the component of the field which is in the direction of AL. Okay, I am calling that EL. Okay, multiplying that EL by DL. After evaluating this, what I'll get? EL is the direction of the field, a component of the field in the direction of AL. So this is EL. So now uh, once I have reduced this, now this problem has been transformed from a dot product dot integral, which we normally call line integral, one dimensional line integral. Now this has been reduced to a simple integrand. Okay, still it is line integral, but earlier we were having dot product, now we are having algebraic product. Now what this is saying to us, let's say we have to move a point charge from point B to point A, and there is some field over there and we want to move it. This integral is saying to us, or this integral, both are the same, these integrals are asking us to divide this path, this line in which we have moved the point charge Q, into an infinitely small differential lengths, the lengths which cannot be further divided into a smaller lengths, and then in the direction of that length take the component of field and multiply that length by that component of field, and then take the next differential length and then take the component of the field in that direction, in the direction of the second differential length, and take the product, and then take the third differential length and multiply that length with the field along that length, and then take another length, and then at the end add all those products. So we cannot definitely consider infinite lengths here. So let me divide this whole path in 3 segments. Your book has decided to divide this length in 6 segments, so you can read the book for a variety. So if this length is, can I treat this length to be differential? No, I cannot treat it to be differential because this is a very big length. If I would join this point by this point, this end of the segment to this end of the segment, I am clearly getting a different line. I am getting a line here, but actually it is a curve. So definitely the length which I have chosen is not differential, rather it is incremental length. Let me call it delta L1. Okay, so this is delta L2, so this is delta L3. I can see that, and this is the direction in which I have moved the charge. Okay, this is the direction in which I have moved the charge. Okay, so I cannot take differential length right now. I am taking incremental lengths here. So if I would do so, what this is telling us, this is telling us that if I want to find the work done, or can I just re-articulate this expression A, which was for moving the charge in the differential length. If I would try to find, instead of differential length, differential work, can I write it like this? Can I write it like this? No, I cannot. I cannot write it like this. Why? Because in differential length it is assumed that you have moved from one point to the point which is next to it, so it is implicit that this length is a straight line. But here we can see that this is, although we are taking this to be a straight line, but actually the curve is like this. So this will only be equals to this if this delta L is very small, approaching to differential length. But what we can do is we can write it like this, that the incremental of amount of work done in moving this charge in this field by this distance can be approximately equals to this if this length qualifies to be called as incremental. Incremental is still very small, but it will be equals to, exactly equals to, if we apply the limit and make this incremental length, convert that to differential length. Okay, so now ये बात तय हो गई कि ये जो segments and these segments are not following the exact path which we actually followed, but let's try to find the electric field at or the work done in moving the charge from here to here along these segments. Okay, so let's say the field throughout this journey, and the field goes beyond this path as well, but I'm taking it to be this field. Okay, and let's say the field at this point 1 is E1, and the field at this point 2 is E2, and this is E3 and E4, and so on and so forth. So after evaluating this, what I'm getting the component of E which is in the direction of AL. So component of E which is in the direction of AL का मतलब क्या हुआ? I have to let's say this is E1, जिस बात में मैंने लंबे arrows draw कर दिए. Let's say this is E2 and this is E3. So drop a perpendicular from E1 on delta L1. This is 90 degrees. So this component is the component. This is actually electric field intensity in the direction of delta L1. And if I drop perpendicular from here to this straight line segment delta L2, if I drop it here, this 90 degrees. So this component is actually electric field intensity in the direction of second component. And similarly for the third, what we'll get this distance is, this component is actually electric field intensity in the direction of the third segment. And remember that evaluating this product will give us scalar, so we are getting the scalar components only. So take this component delta EL1 and multiply it by delta L1. Then take this component EL2 and multiply it by delta L2. So proceeding instead of proceeding along this curve, what we are doing, we are proceeding in straight segments just to get the physical sense of what this line integral is telling us. So this line integral is telling us that the work done, since I have not divided the whole segment into differential lengths, rather I have divided it in incremental lengths. So this should almost be equals to minus q. All these three equations are the same, minus q. Okay, now since I am not dividing this in differential lengths, so I cannot integrate it, because for integration we need to have infinite number of differential lengths. I am dividing this at finite numbers of incremental lengths. So work done will exactly be equals to minus q if I divide the whole path in differential lengths and take this product and then add the product for each of those incremental differential lengths. But since I am not dividing it in infinite incremental lengths, what I'll have to do, I'll have to evaluate this product for these three segments, EL1 multiply by delta L1 plus EL2 multiply by delta L2 plus EL3 multiply by delta L3. This is what I would get. So which is nothing but minus q. ये किस तरह से आया? I have taken the dot product of electric field at this point with delta L1. This is what we got. This is what we had, and we took this dot product to get this, exactly this. Plus, how we got this? We got it by taking dot product of electric field intensity at this point, dot product with respect to delta L2, and same as for the third term, delta L3. This is what we had. Okay, so this is the physical meaning of this expression, which is nothing but line integral. If you study vector, advanced vector calculus, these kind of vectors or integrals are termed as line integrals, and they are again like surface integral or Gauss's law. They are generic to field theory. Okay, they are not specific to electrostatics, but this equation specifically, where we have got the field, electric field intensity, and this charge as this outside variable as the charge. Now this equation 2 is specific for a specific line integral to calculate the work done in moving a point charge, in moving a charge from this point to that point in the field E. Okay, now this work done will become exactly equals to, instead of almost equals to, if I would apply the limit that these delta L's are so small that they can be treated as differential lengths, and differential length से छोटी कोई length नहीं होती, there is no length smaller than differential length, so all these lengths will be the same. So in that case, minus q, in that case I'm not rewriting here, this expression will become this expression. Okay, this expression, which is equal to this. So the whole point of discussing this is to give you a physical sense of what's going on behind this equation 2 or the line integral. That what we do, we divide the whole path into infinitely small differential lengths. Smaller lengths then differential lengths are not possible, and we take the product of that differential length with respect to the field component in the direction of that differential length. We take the product for each of the infinite differential lengths, and then we integrate them all together, we add them all together if we are talking about incremental lengths, but we are not talking about that, we are talking about differential lengths. So we cannot integrate, and we cannot add infinite number of terms, so we have to integrate that. If we are able to do that, then multiply it by minus u, we'll get the work done. But now there is now this topic has been completed here. There is one thing which I should discuss, but I think I should postpone it to the next lecture. So till then, assalamu alaikum.